Okay, so we are talking about exponential functions today, and this may seem a little bit of a review to you guys because we did do an entire chapter of exponential functions in Algebra 2, okay? But of course, we're going to be talking about exponential functions more in the application form as opposed to just, the graphing and understanding it. So we're going to start with what exponential functions are with a quick review, okay? Our objective for today is that students will be able to understand exponential graphs and their properties and use and apply exponential functions to real world scenarios by completing practical applications, okay? So first things first, exponential functions, okay, is a function that operates from multiplication and division rather than addition and subtraction, okay? So it is a function that operates from multiplication and division rather than addition and subtraction. So exponential functions, we have our variable up in the exponent, okay? We have our a times the base b to the x power. The a represents our initial amount, okay? So this is our starting amount. Oh, not gonna want right. Okay, so that's our starting amount there. The B is known as our growth rate, okay, or decay rate. So it could be growth rate or it could also mean decay, okay? So it's a growth rate when it's growing, it's a decay rate when it's getting smaller, right? So this side here, from left to right, you're looking from left to right, and you're seeing that our function is growing in the y direction, okay, as x goes toward the right. So as our function is growing in the right direction there, excuse me, okay, this is known as the growth function. Okay, so this side we have our growth. Okay, that means the y increases as the x increases. Okay. This also means that our b, our base, is greater than 1. Okay? This means that our b is greater than 1. The growth rate or the base of our exponent is greater than 1. Okay? And then we have our decay. The decay, notice that as our x is increasing toward the right, our function, our y, is decreasing toward the asymptote of 0. So as we can see that in the decay, our y decreases as x increases. Okay. And in this situation, our b is less than 1, but it's greater than 0. So b is not negative. Okay, it's always positive. But in the growth situation, it's greater than 1. In the decay situation, it's greater than 1, but less than 0. Notice there are no equal to's. Okay. So, and we're using, I'm going to write that a little bigger here. F of x is equal to a b to the x power. That's the function we're dealing with here. Okay. So then that brings us to our exponential growth. Okay. Exponential growth is when an exponential model grows or gets bigger. So there's something called the growth factor. how quickly an exponential function gets big by a certain factor. Okay. The larger the numbers, the faster it gets bigger. Okay. So our growth factor is usually the B. But if you guys remember, we can rewrite our B with a rate of increase. Okay. So we also had a function that looked very much like this, where we had our A, and then instead of a B, we had 1 plus R to the X power. Okay. In this situation, our B here, right? This is our B. So our B, let me move this up because you might be having a hard time seeing. Our B is equal to that 1 plus R. So the B is greater than 1, right? Because this is about growth. Okay. So B is greater than 1, so we have 1 plus R, where R is our rate of increase. And R is our rate of increase. Because that's what's different from 1, right? If I multiply something by 1, it stays the same. But even if I multiply it by 1.1, right, it's increasing by 0.1 every time, or like by multiple of 0.1 every time. So 0.1 being about 10%, right? So our rate of increase would be like 0.1 or 10%. So every time I'm multiplying it by 1.1, my number is increasing by 10%. So if you multiplied it by 2, which would signify 1 plus 1, it would be 100% growth. Okay, and so we have our function growing as, right? So just to make sure we have this correct, okay, for our exponential growth, our B must be larger than 1. That has to be true in order for us to have an exponential growth, okay? So once again, B must be greater than 1. Okay, so for example, we have an example of an exponential growth model here, okay, our function. We have y equals 2 to the x power. Okay, it's a very simple one, 2 to the x power. And so if we take a look and we plug in our x into our exponent and get some of our values, we can get our points to graph here, okay? So if for 0 here, this is going to be 2 to the 0 power, right? We're plugging it into our exponent. This will be 2 to the negative 1, and so on. Okay, 2 to the 1, 2 to the 4th power. So 2 to the 0 power, anything to the 0 power is 1. 2 to the negative 1 power. Do you guys remember what it does whenever we have a negative exponent?
It turns into the inverse.
Yes, it does. Yeah, very good, Kelly. It turns into the inverse. So 2 to the 1 power would be just 2, right? But 2 to the negative 1 is going to be 1 half. So it'll be the inverse of 2. Yeah, very good. And then so that we have that 2 here, okay? And then 2 to the 4 power, that's 2 times 2 times 2 times 2. Okay, which is going to give us our 16. V2, hun, we are doing our 2.4, 2.5 exponential functions notes, okay? All right, so then if we take this and we graph it, we do have to remember one thing. Notice on all of these examples here, okay, notice all these examples, we do have an asymptote here, right at the x-axis, right? So we do have to remember that with exponential functions, the x-axis is an asymptote. Okay, so y cannot equal 0. This can never equal 0. X can be 0. We can plug in a 0, but notice that whenever we do plug in a 0 for x, we do end up getting a 1, no matter what our base is, right? So it's not going to be 0. So in this situation, we have 0, 1, and then I have -1.5. So I'm going to put that there. And then I have 1 and 2, put that there. And then I have 4 and 16. So 4 and 16. So 2, 4, 6, 8, 10. I'm just going to keep moving up with the spacing. 10, 12, 14, 16. Right about there. Okay. So notice how quickly that shot up. If I did 2 to the third power, we would be at 8. So 1, 2, 3. So 2, 4, 6, 8. Just to give me an idea of how to go there, right? I can even do 2 to the second power, so that's just going to be a 4. I can get that picture right there. But if I did any more negatives, all that would happen was I would literally just get closer and closer and closer to 0 on this end. So if I connect these dots here, and then over here, I'm going to make sure that I'm skirting right by my x-axis, but not crossing it, right? Because it is that asymptote. We do not want to cross that asymptote. Okay. So on the back here, okay, we do have some more information that we want to talk about. And now we're going to be looking at some examples, some real world examples. Okay. Okay. So let's take a look at this. Oh, sorry, moving up. There we go. So it says, let's look at the internet. Okay. The internet is growing faster than all other technologies that have preceded it. The radio existed for 38 years before it had 50 million listeners. Television took 13 years to reach that mark. The internet crossed the line in just 4 years. In 1994, a mere 3 million people were connected to the internet. By the end of 1997, more than 100 million were using it. Traffic on the internet has doubled every 100 days. Okay, so this is based on the Emerging Digital Economy April 1998 report. So obviously it's a little dated, but it still remains pretty useful information and pretty shocking information, quite honestly. Okay, now the question I have for you is this data a good example of exponential growth? Explain. So I want you guys to answer this, okay? I want you guys to answer this on your paper, and then I'm going to call on a few of you to share your thoughts. Okay, so I'll give you guys a few minutes to answer that on your own. Okay, guys. So let's hear from a few people here. I would like to hear from Nick. Haven't heard from you in a while, bud. What do you think? Is this data a good example of exponential growth?
Well, I think it is a good example of exponential growth, as especially as you like look further into the bullet points, as it doubles and like increases more and more as better technology is added to it.
Okay. Thank you for those thoughts. Can you pick a number 1 to 12?
7.
7. Let's see. Seven's absent. Let's go with 6. Because yeah, why not? Anthony.
I said it was a good example of exponential growth because if you look at the statements, the the subjects they're talking about increases with how do I say it? The other
As
one,
time goes on.
yeah.
Okay. Let me ask you guys an interesting question that's kind of off topic. Do you think the fact that radio existed and people were listening to the radio, do you think that that helped television spread faster? And then do you think the fact that radio and television existed helped the fact of internet spreading faster? Do you think they like affected each other's spread? Any I'll take volunteers on that one.
I think yeah, because uh some shows were on the radio before they were on television.
Mm, that's a great point, Kelly. You're absolutely right. Yeah, some shows like series and stuff, right? They used to do, I don't know if you guys have heard, but they used to do like these cool like episodal stories and plays or like skits on radio back in the day. And people would wait all week and they would become like, you know how like you watch movies together with your family? This would literally be like radio listening parties for families. They would sit around and all get together and turn the radio on, and it took a lot of imagination because you had to literally listen intently and then create the image in your head of what's going on. And we're talking like murder mysteries, and it was mainly like mystery stuff or like stories, really really intense, deep, very descriptive stories. um and then of course that was the birth of it, right? That was, and then when we had TV, they turned those into shows, and it required less imagination from people. And we let other people start doing the thinking for us. And then of course the internet now, um anyone can really put stuff on the internet, which is its great success and downfall of for human nature. Okay. Thank you for your shares there. Actually, I think for the majority, can you guys give me a yes or a no? Do you agree that with do you agree with Nick and Anthony that this is a good example of exponential growth? Either yes or no, just telling me if you agree or disagree. All right, great job. Will, welcome. We are doing 2.4, 2.5 exponential functions. Um, we're on the back of the first paper. Okay, so we want to determine if the following is an example of exponential growth. Okay. If so, we want to find the growth rate. Okay. If you guys remember how we determined the exponential growth, we wanted to try, we essentially determined it by determining if it had a growth rate or not. And if you remember, the way that we found our growth rate was we took each y, right? Let's say I'm gonna use subscripts here, okay? And we put a y over y, but we made sure that whatever the bottom y was, the top one was the one right after it. Okay, so it was like y sub I plus 1 over y sub I, aka this y over that y, this one over that one, this one over that one. And of course, this only works if our x's are using the same interval. Okay, if our x's are moving in the same interval. So 5, 10, 15, 20. In this case, they're moving in intervals of 5 here. Okay. So if I want to determine my growth rate, I essentially take my y's and I'm going to do 1.5 over 0.5. So 1.5 over 0.5, and I divide that. Okay. 1.5 divided by 0.5 is actually 3. Now, if I do the other few of these and they end up having the same growth, same number here, then we have an exponential growth, right? Or we have an exponential function here. So now I'm going to do, so I did 1.5 divided by 0.5. Now I'm going to do 4.5 divided by 1.5. So 4.5 divided by 1.5. Okay, so it's the next divided by the previous. And that's also a 3. 4.5 divided by 1.5 is also a 3. Okay, but I want to make sure that all of the points that were given to me follow the same. So next I'm going to do 13.5 divided by 4.5. Okay, and when I do that, I also get a 3. Okay, so this means I have a growth rate. So this means that it is an exponential function. Okay, so this is an exponential growth with a growth rate of 3. Okay, with a growth rate of 3. So one way to determine if there's a growth rate, if it's an exponential growth, is by doing the division of the y's. Again, making sure that our x's, right? In this case, x's must move with the same interval, which means that the spacing between each of the x's, I'm sorry, you guys can't see that. The spacing between each of the x's there should be the same in order for you to be able to do this. Okay, so they could be moved, if the x's could be moving by 1, it could be moving by 2s, it could be moving by 3s, whatever, as long as it's a consistent one. It's a consistent interval for what points you're using. Okay. That trips a lot of kids up, so you want to make sure you're paying attention to that right there. Okay. Sometimes we're asked to determine if the following graph is an example, right? And we're looking at the graph itself. So for the next example here, we have find the exponential function. Oh, I'm sorry, I read the wrong example. We have determine if the following graph is an example of an exponential growth and explain why or why not. Okay. We could technically, if this was like a clear enough graph, we could technically look at the points and then do this whole system that we did up here. But a lot of times we can tell whether it's an exponential growth or not just by looking at the graph itself. So usually exponential functions, right? There is like a slower paced growth followed by a very sharp increase. Okay. So we have like something that's very consistent, and then all of a sudden we have it shoot up. Okay. So if you can see here between just these few years, we've increased quite a bit significantly. So over here, right, we're talking about number of internet hosts and number of internet hosts here. So we go from 0 million to 350 million between the years of 1992 to, I would say, about 2000. This is 2004, so maybe 2005 here. This could very well be 2005. Okay. But we can see that it's very minor growth, minor growth, minor growth. Over an 8-year period, we have a very minor growth. And then around 2000, it starts increasing very rapidly. Okay. So because of this minor, and then a rapid increase between a short amount of time, okay, we can say that this is an example of exponential growth. So yes, and we write in complete sentences. This is an example of exponential growth. And we do not forget that we need to explain why. Because, okay, there was a rapid growth between the years of, and you can say 2000, you can go a little bit earlier and say 98 or whatever it is. So you could technically say 2000, from the year 2000 to, 2005 or 6, between the years of 2000 and 2006, right? You could even go a little further because it looks like the growth is kind of starting over here. So you could have even said from 1998 and on, right? So yes or no, explanation why. Okay. The next example is a bit of an algebraic one. Okay. So it says find the exponential function. So now we're finding an exponential function when the population of the popular town of Smithville in 2003 was estimated to be around 35,000 people. Okay, with an annual rate of increase, okay, so annual rate of increase of about 2.4%. All right. So we have to remember rate of increase or growth rate, right? We're talking about this form of our function because we're given a rate of increase here, right? So we're using our a 1 plus r to the x power. And the rate of increase is given to us as a percent, but we can't put it as a percent into the function, right? So we're using this guy. We're going to just write our function here. Okay. It says that their population in 2003 was 35,000 people. So that's our A. Okay, so 35,000 people. That's going to be our A. That's our initial starting amount because that's what they're telling us. Okay. And then they have an annual rate of increase of 2.4%. So the R here, okay, is 2.4%. But as I said, we can't input the R as a percent. So we need to change that to a decimal. Okay, so we're going to take our point and we're going to move it two decimals to the left. Or you could just take 2.4% and divide it by 100, which does the same thing. Okay, so I want you guys to pay attention. Okay, do not assume. Pay attention to the work that you're doing. Notice 2 decimals to the left, 2 places to the left. Add the 0 there. So this is a 0, this is a 0.024 that's going to go into our equation here. Okay, so our equation, if as we plug in, it's going to be y is equal to our a, 35,000. Okay, open the parentheses. We have 1 plus 0.024. Okay, close the parentheses, x. Okay, so this one here, okay, I want us to understand, this one acknowledges the initial, it acknowledges the initial population, okay, because 35,000 times 1 is still 35,000. So it acknowledges that initial population. The 0.024 acknowledges the growth that's happening from the initial 35,000. Okay, so when I simplify this, I'm just going to get y is equal to 35,000. And then I'm going to combine that. 1 plus 0.024, so that's going to be 1.024 x. And so now this looks like my a times b to the x power, right? So I want to write that little something. So since each year increases by a 0.024 rate, we add the 1 to the rate to acknowledge the current population. So my apologies. Here you go. Okay, flipping over. Oh, look, we have another question up here. It says, predict what the population of Smithville was for 2007. Okay, so our function here was y is equal to 35,000 times 1.024 to the x power, right? So we have to make sure we pay attention to what year the starting population was from. The starting population was from 2003. So if I'm trying to predict the population in 2007, I need to calculate how many years 2007 is from 2003, because that was when we had our starting population. So from 2003 to 2007, we have 2004, 2005, 2006, 2007, right? So 4 years. So our X here is going to be 4 because it's 4 years from 2003. So all we do is just plug that in to the fourth power there. Okay. That 35,000 parentheses 1.024. I'm going to use my little caret right over here. Oh, caret here. That puts it up into the exponent. Put in my 4. There we go. Okay, so it'll be, and we're going to round that because there's no such thing as 0.91 of a person. So we'll round that to a whole person, right? So this is going to be approximately 38,482.91, which is 38,483 people. Okay, so the population in or of Smithville in 2007 was approximately, because we approximated, we want to write approximately 38,483 people. Okay. Okay. So then we're going to look at decay. So similar activities, similar idea. Okay, but for decay, where our numbers are getting smaller. Okay, for decay, our function is getting smaller and our numbers are getting smaller in decay. So for exponential decay, our model is getting smaller by a certain factor. Okay, and the decay is how quickly an exponential function, the decay factor, I'm sorry, is how quickly an exponential function gets smaller. Okay, the larger the numbers, the faster it's getting smaller. Oh yeah, the larger that your number that you're starting off with, right? The larger the initial amount, the faster your function is getting smaller here. And so you also you have your decay factor, right? Excuse me. In this case though, our function is very similar to that of growth, but instead of adding the rate to 1, we are subtracting the rate from 1. Okay, so our B in this situation, okay, is 1 minus R. So our B is 1 minus R, where 1 again accounts for your starting amount. It's your initial amount. The minus R, right? R is your decay rate. Okay, or your rate of decay. And you're subtracting the R from here so that you're saying I start with my initial amount and then I subtract this much from it, right? So it's a matter of starting with the initial and then subtracting however much is going away essentially. In this situation, our B is less than 1 but greater than 0. Okay, so it's between 0 and 1. Okay, so B must be between 0 and 1. Okay, and notice that we are starting high and rapidly getting smaller. Okay. There's a typo here in an example. Determine if the following is an example of exponential decay. If so, find the decay rate. Okay. So over here we have 0 and 192, 1 and 96, 2 and 48, 3 and 24. So notice my x's this time are increasing by 1. It doesn't really matter what they're increasing by as long as it's a consistent increase. And I'm going to do the same thing. I'm going to take it's not about big or small, right? It's about second over the first, third over the second, fourth over the third, okay? So in this situation, I'm going to do 96 over 192. Okay, 96 over 192 is a 0.5. So if the rest, and notice how it's between 0 and 1. So if the rest of them are 0.5, then I do have an exponential decay happening here. So then I go to the third over the second. So 48 divided by 96. Okay, and that also will be 0.5. Okay, 48 divided by 96. Yep. And then lastly, fourth divided by third. So 24 divided by 48. Okay. And that is also 0.5 or 1/2 if you look at it that way. It doesn't have to be a decimal. Okay. So in this situation, I have, yes, it is an exponential decay with a decay rate of 0.5. Okay. Okay. This example is very much like the population example. Okay. Population is usually a exponential growth example. Exponential decay examples usually tend to be about cars. They tend to be about things that depreciate quickly. It could also be about phones because you buy a phone for $1,000, but if you want to sell it back like 2 days later, it's down to like $600 or $700. It's really, could definitely be about phones. It could be about most technology, but so it's anything that drops in quantity, right? So biology, a lot of bacterial growth stuff is exponential growth. A lot of vaccine stuff is about exponential decay because it's about killing the vaccine in the cells. So different biological applications as well. Matt bought a new car at cost, okay, at a cost of $25,000. The car depreciates approximately 15% of its value each year. So the car depreciates approximately 15% of its value each year. Okay, this is your R right there. Okay, how much you bought the car for is your A. They actually take it a little further. They say, how much will the car be worth in 10 years? Okay, so you could take 15% of 25,000 and then subtract it from that and then do the same process 10 times. So multiply 25,000 times 15%, figure out how much that is, and then subtract it from 25,000. And then that next number, you can take that, multiply it by 15%, figure out how much that is, and then subtract it from that number. And then take that number, multiply it by 15%, figure out what that number is, and then subtract it by 25, or by however much was there. Or you can write a decay equation. So our decay equation is y is equal to a times 1 minus r to the x power. Okay. Again, minus because it's depreciating, right? That's a dead giveaway. The A is 25,000. The R is 15%. And again, do not forget to change this into decimal form. So 15%, take that, my decimal that's there, decimal, decimal. So we move it over twice and we get a 0.15. Okay. So when I plug this in, I get y is equal to 25,000 times 1 minus 0.15 to the x power. Okay, so I have y is equal to 25,000, and then I'm going to simplify the 1 minus 0.15. 1 minus 0.15, and that's going to give me a 0.85. Okay, you really got to be careful with your decimals. Okay, so 0.85. So this 0.85, notice how this 1 disappeared, right? The 1 is no longer there. So in the growth, that 1 was, it was our b was a greater than 1 because that 1 acknowledged the whole, right? The starting amount. In this case, we're talking about the amount that's going to be left over. So if I did this for the first year and I did 25,000 times 0.85, this is how much the car would be worth after the first year, right? So I'm calculating how much is left over. I could have done this by doing 25,000 times 0.15. This is how much it's losing. So, and then I could have taken 25,000 minus 3,750, right? 3,750, and I still get that 21,250 that I got earlier. Okay. Now, as I was saying, right, if I take 21,250, multiply by 0.15 again, and then take that and subtract it from that, that would then give me the second year's remaining cost or remaining price. But this is a process, right? For first year, second year, it might be easy. But for 10 years or even more, having this exponential model here, this exponential decay, where I'm literally just asking, okay, this is how much is going to be left over of the price every year. So if I want to know how much the car is going to be worth in 10 years, that's going to be 25,000 times 0.85 to the 10th power. Okay, so when I do that, okay, hit enter. So again, if you want to put any exponent number, you're using this caret right over here. Okay. So 4,921.86. And I stopped it at the 100th place because we're talking about money here. So 4,921.86. Okay. So in 10 years, oh no, give me a second, sorry. In 10 years, the car will be worth about or approximately, okay, $4,921.86. So if someone was trying to sell this car, they might list it for about $5,000. If they wanted like a fair price. Okay. Hmm. Okay. So I think from what I remember, we have an activity for today's class. It is called I think I'm gonna do, what do I have on the thing? Hold on. From what we've covered thus far. I want to make sure I'm assigning you guys what we've covered so far. Let's go back here. I feel like this activity should go here from what we've been able to cover thus far. So, you have an activity here, 2.4-2.5b, okay? Determining growth and decay. So for this one, I think this is a better fit for what we were able to cover so far as classwork goes, and it should not take you guys very long, okay? So I want you guys to do the 2.4, 2.5b. This one we'll do after the day 2 lesson. So I'll edit that. But then you do also have a homework assignment. Yeah, I don't want to keep downloading those. Oh, wait, no, I need to keep downloading those because I don't have my USB in. You do also have a homework assignment here. Okay, understanding the properties of exponential functions. Okay, so this is about graphing and understanding increases and decreases. Both of these are very good for helping you guys understand the differences between growth and decay. So I'm gonna, give me a second, let me edit the home page real quick. And I'll switch those activities so that you guys are not confused. What is happening here? Give me a second. Okay, so we had the 2.4b for the first day of lessons, and then we will have 2.4a for the second day of lessons. That one. Okay. Yeah. So you're gonna do this determining growth and decay in the homework 9. Okay. Let's make that due by like the end of the week. I'll put up the upload links here. I'll also put up the upload link for the how tall is he activity. Okay, I'll do that today. And of course I'll extend the deadline so that you guys are not getting dinged for my mistake there. Okay. So refresh the chapter 2 page. And it should reflect that today's activity is the growth and decay one. Okay. Any questions? Let me know if that's too much, the activity and the homework. All right.